have transmissions here. He's going to be leading it. And yeah, if you have any questions, feel free to pop them right into the chat and he'll try to get to them at the end. But if not, then you can reach him on the Dev-Tools chat. Okay, transmissions, you can take it away.
Cool. Does everyone hear me all right?
Yep, you sound fine.
Awesome. Okay, so yeah, as explained, this is the kind of Dapptools intro talk. You see a kind of compendium of Dapptools excitement tweets. So if you've already tried Dapptools, hopefully you can learn something from this talk. If you haven't, buckle up. How do I move slides on? Okay, there we go. Really quick, I am a developer at Rari Capital. I'm a Dapptools convert and vocal shill on Twitter. I make Solidity libraries sometimes. You can find me at Transmissions11 on GitHub and Twitter. Just going to acknowledge Georgios, who helped with some of the images on this talk, and also some of the content. So this talk is for developers who are already comfortable with hard hat. If you haven't started with Ethereum at all, you might want to go learn about some of those basic concepts first. But otherwise, yeah, we're going to take to the next level. So I'm going to start off by posing a question. What do these two contracts have in common? They add up to the top Ether balance contracts on Ethereum, the ETH2 deposit contract and the wrapped Ether contract. They add up to hold like 13% of all ETH in existence, a casual $60 billion. As might be obvious from the talk, they're both built with Dapptools. You can see in the consensus specs repo, they're importing DS test, which is the Dapp Hub test framework. And same with the WETH repository. So if the two biggest contracts on Ethereum trust Dapptools, maybe you should consider trusting it too. So what is this Dapptools thing? It's tooling for writing, testing, fuzzing, and deploying Solidity smart contracts. You hopefully know at least 3 out of 4 of those things what they mean. It was developed by the Dapp Hub team, which was like MakerDAO's engineering division back in the day. That's Andy in the top right presenting it at like DevCon 3. It's been used by the ETH2 deposit contract, MakerDAO, Fractional, Reflexer, Pickle, Maple, countless others. It's got almost 1,000 stars on GitHub right now, and I just gave some logos here. Really quickly out of the way, it's like kind of a replacement for hard hat. You can use them in the same project, but they kind of serve the same role. And you can get mostly the same features out of both, but Dapptools has some couple bonus ones that I'm really excited about, and I'll be showing you in the talk today. So really quickly, like, why not hard hat? You might really like hard hat. So why should you consider switching to Dapptools? First of all, nothing super wrong with hard hat, like no shade intended at all. But writing tests in JavaScript is just not enjoyable for me. And yes, that includes TypeScript. I'm sorry. There's just way too much boilerplate. There's like hundreds of files if you look in like Paul's Ethereum template, which is great, but there's like a million dot files and config, and it takes a while to install, and there's a pre-commit hook. There's all this stuff about managing big numbers, BNJS, BNs, like JavaScript now has its own native big number. This is all a pain to convert between. And when you're just trying to test your Solidity smart contracts and you have to like operate in this whole like JavaScript world of converting these numbers, it really kind of takes you out of the mood. And it's also just slow for complex tests because you're running, JavaScript isn't a fast language. And some of the time you're actually interfacing with the kind of EVM over RPC even, which is going to be even slower because you're making network requests each time. And the main reason I don't like it is just because it's context switching. I want to focus on my Solidity. I don't want to be debugging some random issue with big numbers or other JavaScript stuff that's kind of in the way. It's kind of a whole level, different level of abstraction, which is separated from my smart contracts. And then the other thing is not enough tools. So you might be familiar or might not with fuzzing and symbolic execution. These are some really advanced testing tools and get you a lot more confidence that your code works as intended. But currently they require, you need to use separate tooling to access them, like Manticore or Echidna. These are separate from your hard hat project. They're kind of a pain to set up, especially if like you have to you're writing similar tests for both, but they're in entirely different languages in one project. And because of this, not many devs kind of integrate these tools, and they're really awesome, and they can save your contracts from getting hacked for millions of dollars. So if we want devs to write more secure code, we need to give them better tools. Dapptools is that better tools. So, all All right, Dapptools 101, like kind of why Dapptools now? No JavaScript, you write your test in Solidity. For some of you, that might actually sound pretty bad. Like I know a lot of people kind of have this grudge against Solidity because it's like, well, it's not JavaScript, it's not super powerful. Like, okay, there's just kind of a really nice, I think you'll find that there's a really nice just kind of vibe with being very close to your code and not having this layer of abstraction that is JavaScript most of the time. So you write your test in a function in a .t.sol file, which indicates it's a test. Here's an example of a kind of test function up here. And then we got features. It's fast. It's really fast. You can run builds in less than half a second. You can run a whole test suite in seconds or two. You can run invariant tests, symbolic tests, and these can all run in at most a couple seconds, and with fuzz test a little more. But it's fast. It's low boilerplate. I'm going to show you that we can spin up a batteries included Dapptools project that is like completely production grade in 10 seconds with no kind of templates necessary. It's got powerful cheat codes, which we'll explain more. It's got gas snapshotting, mainnet forking, stack traces. Here's an example of stack traces. Look, you can see all the events emitted, functions called, where it reverts. You've got a visual debugger, console.log equivalent. I know many of you probably love console.log. Deploy and verify on Etherscan, install dependencies from any GitHub repo, built-in test coverage, invariant tests, property tests, symbolic tests, and it's all through the command line. So you can kind of build your own kind of abstractions on top of Dapptools like really easily just with bash scripts. So really quickly, Dapptools has a lot to offer. It's actually a collection of tools. There's Seth, which is this tool like that lets you read and write from the chain. Dapp, which is what we're going to be focusing on today, which is for compiling, testing, and debugging smart contracts. And then Dapp kind of uses this lower level tool they've written called HEVM, which is like a custom EVM implementation for designed around debugging and symbolic execution. So we're going to focus on Dapp and what the rhythm for building and testing smart contracts look like. But I encourage you, and maybe I'll have a follow-up talk sometime about trying to explore Seth and HEVM on your own. So really quickly, I'm probably going to be going at a pace too fast to follow along, but just I'll have these slides. I'll send a link at the end, so you can kind of use this as a reference. You install Dapptools, you install Nix first, then you install Dapptools with this shell installer. Make sure if you're on an M1 Mac, you do this in a Rosetta terminal. Okay, creating a new project. It's really this simple. You create a new directory, you enter the directory, you call dapp init, boom, you're done. Those are two tests that are already spun up and running. That's literally it. In 10 seconds, we spun up a fully functioning batteries included Dapptools project with two tests that just ran. And look at that little time window at the bottom. That took 6 seconds for the tests and the spinning up of the project. So the speed to getting started with Dapptools is really second to none. So compiling, you see this is the kind of default Dapptools project structure. We have an SRC folder, some Git configuration. But the main thing you're going to want to focus on is the SRC folder. We have the test project.sol, which is like our contracts, and a test project.t.sol, which is our tests. I purposely edited the kind of default to have a broken, some broken code that doesn't compile. You test that by running dapp build, and you'll see this kind of colored compiler output that tells you, look, you didn't declare these identifiers. That's pretty obvious. And yeah, this is less than half a second for a build. So let's do some basic testing. So if we go back to that function, we remember we have this add x plus y function. How are we going to test this? Well, first, let's kind of understand our tests. So in the test project.t.sol file, this is where we put our tests. You can see that here, let's keep it simple for now. You can see that we have this kind of test project contract. It inherits from this DS test thing. It's got a setup and it's got a test. So what are all these? The red stuff is the Dapptools testing framework. It's kind of the Solidity library you import that has these helpers for you. You declare the kind of contracts you want to test using state variables. You have a setup, which gets run before each of your tests. And the cool thing about setup, which makes Dapptools so fast, is you may be used to like fixtures in Hardhat, which like you have to explicitly declare a kind of state you want to roll back to. Dapptools automatically just, it runs your setup once, it kind of caches that state and just rolls back to it for each test, which makes it much faster than rerunning it each time. You can see with the cyan, we have a test, and then we have like an assertion inside that test, which looks kind of similar to normal Solidity assertions, but there's some more powerful versions that we'll see. So this is how we're going to test our add function. You see we call our project contract and we call add. We pass the arguments 1 plus 2. We assert that this is true, that it equals 3. So how are we going to actually run these tests? Well, we run the dapt test command. You put this in your terminal in the same directory, and you'll see this output. You'll see it runs the test, and it gives you the gas usage of the function, which is super dope. And it tells you that it passed. All right, that was pretty easy. What did that take us? 15 seconds probably to get that started. And you can also use this verbosity 3 flag to kind of see a full stack trace for the test. You can see that it ran setup, it created our test project, it called add, and then it returned 3. Okay, now let's try making our test fail. We changed this from 3 to 4. We introduced a bug, so this should fail, right? We run dapt test again, and it says assertion failed. The problem is this error kind of sucks. Like, maybe for now, because it's a really simple test, we can know exactly what's going on. But if we've got really complex tests with lots of different values, we really want to like get a better error message than this. Luckily, Dapptools to the rescue, DS test has a crap ton of assertion functions that you could take advantage of that are much, much better. So we can swap out our assert true for assert equals, which all you do is you just kind of put the thing it should be equal to in the second as the second argument. And now when we run our tests, we see this beautiful stack trace that shows us that the uints didn't match what we expected it to be and what it actually is. Okay, now let's make a new function. Say we have this function called noFunAdd. noFunAdd doesn't let you, it acts like add, but it doesn't let you add 2 values that would equal 69 or 420. And it will revert with you cannot have fun. So how are we going to test this? How do we test for reverts? So let's first just like make a normal test like this wouldn't revert. We have this test add no fun numbers. We assert that 0 plus 69 equals 69. But this is going to fail, right? Because our thing reverts. So yeah, just as expected, if we run our test with dapt test again, we can see that it reverts. Test add fun no numbers. We can see no fun add. It reverts on line 12 in there with the you cannot have fun message. So how are we going to like assert that it's reverting here, right? It's probably simpler than you're expecting. That's it. You just prefix the test with fail. So test fail indicates that the test will only pass if the function reverts. And now when we run it, we can see it passes. So test fail makes the test kind of act in the inverse of a normal test. A normal test will fail if the test reverts or an assertion is violated. Test fail will fail if an assertion is not violated or the test succeeds. And right, so this is demoed here. If we like no fun add 0 plus 1 won't revert because that's not one of our funny numbers. The test fails because it didn't revert. All right, so here's the problem with these kind of concrete tests that you're used to in Hard Hat. And you just saw, okay, well, this is pretty cool in Dapptools. I can write it kind of some similar way. But here's where Dapptools really takes it to the next level. So this test doesn't really give us a ton of confidence our add function is correct. Like, what if the add function just always returns 3? Our assertion wouldn't catch that bug in the code. To be really sure our function is correct, we need to try lots of inputs on it, right? So we could duplicate it a bunch of times. We could have 1 plus 2, 1 plus 3, and assert on all this. I mean, it's better, but there's still millions of combinations we aren't trying, right? So this is where fuzz testing comes in. What if Dapptools could generate random inputs for us? So here's how you do that. You have this test add numbers function. This is our normal test, but we adapted it. Now it's taking arguments. It's taking a uint, it's taking another uint, x and y. We call project.add with those uint values, and then we assert that it's equal to x plus y. Test functions can take arguments. Dapptools is now automatically gonna like try random uint arguments on this test function for us. We don't have to define values in advance. So if we run dapt test, you'll probably be surprised to see that it fails. Okay, what the hell is going on here? This is a bit of a complicated error message revert screen, and our function looks correct, right? It's just adding x plus y. So if we kind of zoom in on this, you'll see that it failed. It's got red, and you see this big stack trace. And it shows us a kind of counterexample, the inputs that caused the test to fail. You can see it failed due to a revert. And tests can either fail because their assumptions broke or a function call reverted. In this case, it was a revert. This is a solidity panic, which means it's kind of a solidity compiler check was broken. We can look in the documentation. Since it ends with 11, this means there was an overflow that happened. And now this input starts to make sense. We have this huge, we're trying to add these two huge numbers together, which is going to cause an overflow and cause our test function to revert, which is going to lead to Dapptools thinking that something is wrong. So we can solve this pretty easily just by changing the arguments of the test function to be uint128. If both parameters are uint28, the max uint128 plus the max uint128 cannot ever, like it can't exceed uint256. So if we run our test again with these modifications, they pass. It ran 100 times. It's pretty neat. Dapptools is spamming our tests in essence with a bunch of inputs, which gives us more confidence our code is correct. By default, it tries 100 different inputs. You can increase it with this fuzz runs flag. Now it tries 10,000. Okay, this is cool, but it's just, it really isn't good enough yet. Like we need to be sure every possible combination works if we want to be sure our contract works as intended. This might seem kind of trivial with like an add function. You're like, okay, I mean, it's adding two numbers. But when you're dealing with your kind of, DeFi project or whatever, where there could be a math bug somewhere that could wipe the entire system, you really need to be sure that every last number is accounted for. The kind of problem with doing this with fuzzing is beyond a certain point, like every fuzz run takes some time. And if you want to assert 10 trillion fuzz runs, that's going to take 10 trillion years. All right, how do we fix this? Symbolic executions. This is kind of an advanced topic. Symbolic execution is a way to test code for correctness. You as the developer use it the same way you use fuzz tests. You define inputs, you run code with the inputs, make assertions. Dapptools will let you know if it can break your test and give you inputs on how. So we're not really going to go into depth about how symbolic execution works, but just kind of under the hood, it kind of converts your code into math, and then it uses a math solver to kind of point to places, to kind of find ways to all the states your code can be in. And if any of those states violate some of your assertions, Dapptools lets you know. We're not going to go into detail. So how do we make our boring old add numbers test a symbolic test that will basically, in effect, try every possible input? Do you catch that? We just renamed the test from test add numbers to prove add numbers. That's really it. So yeah, Dapptools makes it trivially easy to turn any fuzz test into a symbolic one. So now if we run dapp test, you see it passes. And Dapptools is able to kind of reduce this down to math, kind of solve it, and show that no branches kind of violated our assertion. This is super sick. And now, assuming there aren't bugs in Dapptools or the solver, we have 100% certainty that our assertion holds over every single possible input that a system can be in. So why should we ever use a fuzz test if symbolic execution tries every input and is still fast? Like, can we just throw away test and use prove? Symbolic tests are great, but sadly, they can't be used for everything. They're constrained by the complexity of the code they're testing. Blah, blah, blah. Basically, like the more complex your code is, the more states it can be in, and the more kind of math equations the solver has to find. So symbolic execution basically becomes infeasible beyond a moderate level of complexity. So use symbolic tests for like math functions, which don't really have a lot of possible branches or isolated parts of your code base. But you're probably going to end up using fuzz tests for larger parts that are too complex to symbolically execute. Just a quick comparison. So fuzzing, you get fairly strong assurance. It depends on how long you run the fuzzer. And there's no limit to the complexity of tests it can run. With symbolic execution, you get near 100% assurance, but it can only be used for kind of simpler code. Let's discuss one last Dapptools test type, invariants. Invariants let you test assertions about your higher level state relationships. For example, like the total supply of the wrapped ether token should always be equal to its ether balance. So invariant tests allow us to kind of just write that and not define all the functions Dapptools needs to call. We just kind of let Dapptools explore our contracts on its own and test the assertions to ensure they're always true. So how do we do this? We have this contract called increase. It is a value state variable, and it has a value times 2 state variable, which we want to assert is always twice the value of value. So we can use we know we can use invariant tests. So how are we going to do that? Invariant tests look similar to normal tests. They don't have arguments, and they're prefixed with invariant instead of test or prove. Dapptools is just going to look at all the contracts that are stored in your test contract and call them with random values. So we can write our invariant like this, invariant times 2. We have an assertion. We say that the project.value should always be equal to value times, it should always be, value times 2 should always be equal to twice project.value. So that's a typical assertion. If we run this with dapptest, we'll see that it takes like about 6 seconds. And it tried over 2,000 call combinations, and after none of them did our invariant break. So this is pretty good. Like, we got some nice assurance about that. Wait, did I just? Oh, okay, yeah. So here we have, so let's add a new function to our test called break the invariant. Not to our test, but to our project. So we have this break the invariant function. It takes a uint8. If the number doesn't equal 69, it's going to revert. But if it does, it's going to mess up value times 2. So if anyone calls this with 69, our invariant will break. So let's see if Dapptools can catch this. We're not going to change our test at all. Yes, it did. We ran dapptest, and we can see our invariant failed. And we can see this kind of big stack trace, and we can see it found a way to break it. It expected 3, and it was actually 4. So you can see in the red all of the calls it's making. It first called increase, then it called break the invariant with 44, and that reverted, and then it called it with 69, and then it saw the invariant broke. So we can see it first tried calling with the wrong number, and then it called it with the right number. And after every call it makes, it checks the invariant holds the first 2 times it did, and after calling break the invariant with the right number, it broke. So this is pretty neat. We didn't have to write any specific test logic testing the break the invariant function. Dapptools just kind of found that for us, which is pretty amazing. So it held each time except for the last. Okay, now we're going to get into some kind of assorted stuff. If you're a hard hat user, you probably have fallen in love with console.log. Where's your console.log? Don't worry, it's right here. So we have these kind of, it's slightly different. You use events, these log events, which get printed to your stack trace. It'd be trivially easy to make a console.log type library that just wraps these events if you don't like it. If anyone wants to work on that, reach out to me. But yeah, so you just emit log uint, which is the type we're logging here. So we log an unsigned integer, and we'll see if we run our test that it shows our value here. And basically, these logs only show up if your tests fail by default, but we need to use a verbosity of 2 to see logs for passing tests, since the test isn't failing. All right, you might be wondering, okay, this is kind of confusing. Can I give this log a label? Wait, where did my label slide go? The answer is yes. You just use log named uint with the label. So there's a log for every function type. All right, some other features. You have built-in coverage, so you can have all your tests written, and then you can kind of run dapptest coverage, and it gives you this output that shows for every line of your code, does a test at some point touch that part of the code. So you can see here we have coverage for this file, and in the console it shows us highlighted in green the lines that are covered. So everything's covered here. But here in this function, not everything is covered. So red areas indicate that code is not reached in any of your tests. So you need to write some tests where that code is written, and then it'll turn green. This is really sick. I'm sad I have to gloss over this because we're kind of running out of time. But dappdebug is you can run dappdebug in your console. It opens up this kind of visual menu where it lets you select which test you want to debug. You select one of them, and it gives you this really kind of, at first confusing, but really powerful debugger view where you can kind of step opcode by opcode through your code. You can see we have a stack trace on the right that updates as you step through your code. We see which part of my code is executing in bold. You see a live view of the EVM stack. And this is really useful for like seeing why your code takes so much gas. You can see all the opcodes that are run and be like, oh, there's an extra S load here. Like, let's cache that. And it's also useful for seeing what part of your tests execute when things are breaking. But is there mainnet forking? I see this question a lot, and for some reason, people assume Dapptools like wouldn't have mainnet forking. It definitely does. You can see this in the docs. You just run dapptest with the RPC URL flag. In this case, we use like Coven and Fura, and then your tests will run in that environment. You just write them as normal. What if I want to change the current block, the current timestamp, update a storage slot? Cheat codes. Dapptools is this thing called cheat codes. They're implemented basically as function calls to the special address. There's set block timestamp, set block number, update a storage slot, load from a storage slot, and this kind of other crazy stuff. Here's an example of using them. We define this kind of HEVM interface. We define the HEVM address. And then in our test, we can call HEVM.warp, and this moves the block timestamp 5 days in advance. So this can be used for testing functions that depend on the time, right? Like compound interest. Yeah, so that was all I want to go through in terms of slides. I'd suggest starting with, I know I said no templates are necessary, but there are some kind of helper scripts you can get. And especially if you're using something like VS Code, which doesn't recognize Dapptools projects by default, I'd recommend trying out Georgios's Dapptools template. Dapptools doesn't end with just the dap command like I showed you. Make sure you try out Seth. We've compiled the list of Dapptools projects to learn from as examples in this Rajiv Poe awesome Dapptools repo. I'm a maintainer. You can find the slides for this talk at tinyurl.com/dapptoolstalk. And if you have any questions, please reach out at https://dapphub.chat. So this is DappHub's or Dapptools is a kind of chat room. There's a lot of awesome developers in there ready to help you out. I'm one of them. I'm quite active in there. I say good morning every day in the random channel. Please join. Authentication is broken for everything except Twitter right now. So don't be disheartened. Just make sure you're logging in with Twitter in there. I'm active. You can ask questions about this talk. Just ping me or DM me. I'm at T11S or Dapptools in general. So that's your place. Thanks for listening. That was our quick Dapptools overview. I think I have about at least like 4 minutes to the end of this talk. I might be able to abuse my little 5 minutes I can use after to give a quick demo of how we'd write and test the WETH function. Not the WETH function, a wrapped Ether contract. So I'm going to try to go ahead with that. So here's a test project I just spun up in advance. We can run, so we have this WETH test, we have this WETH. So I'm going to start out really simply by, so this is one of the awesome features of Dapptools is you can install GitHub repos as kind of dependencies. You don't need NPM modules. You can just do https github.com, or wait, you can just type it as like this. You can type Rari capital /soulmate. So this is kind of a library of Solidity functions. Oh, I have to commit this on Git first. Sorry, it's one little quirk. Add an existing repository, desktop, test project. We can add this repository. We're just going to commit this. Okay, so we can install the Soulmate repo, which is like a kind of Open Zeppelin replacement in some ways. It installs it into our project, and now we can import it. So I'm going to import the ERC20 base contract from Soulmate. So that you just do it like this: Soulmate tokens ERC20.sol, and we're going to have our WETH contract inherited because wrapped Ether is an ERC20. They're going to want it's going to want a name, so we're going to name it wrapped Ether. We're going to give it a symbol, WETH, and we're going to give it 18 decimals. So this is the typical Ethereum decimal scheme. We're going to give, and now we don't need any constructor because WETH is pretty simple, but we're going to need to implement a deposit method. So deposit is an external payable function. And just to save a little time, I have the code already implemented down here. So I'm going to put this in here. I have this other safe transfer library, which is just kind of for handling ETH transfers safely. All right, boom. So we have a minimal version of the wrapped Ether library implemented here, of the wrapped Ether contract implemented here. Now let's test it. So first of all, we can just see our test over here. We can build the contracts really quickly to make sure everything works. So we type that build in our console. Works perfectly. We see that little check mark, so we know it's working. Let's implement a really simple concrete test. We can test deposit. So our test contract actually starts out with Dapptools with a crap ton of Ether in it. So we don't need to like get Ether anywhere. We can just write WETH deposit value, and let's do 1 Ether. And now we'll make an assertion that we now have our test contract, which it can be accessed under address this, has 1 ether of WETH. So the WETH token is minted when we deposit 1 ether of WETH. So we run dap test. Boom, our test passed. So you're probably thinking like, okay, you just showed us all this fuzz testing stuff. Why don't you put it to work? Let's put it to work. So we'll do uint 256 amount to deposit. One caveat here is, since we don't have unlimited ETH that starts out in this test contract, we have to ensure that our balance, that this amount is not greater than our balance. So if this amount is greater than our balance, we exit the test early. And now otherwise, we can just replace all of our hard-coded uses of 1 ether with amount. And if we run dap test, you're going to see it tried 100 combinations there and our test passed. So that's a really simple fuzz test. And if we want to like be a little more confident, we can bump this up a bit, and you'll see that it's just going to try a grind basically our function for any values you can find that break it. And it passed. Our WETH implementation is looking pretty good. I was going to demo withdrawing, but just to kind of speed this up a bit, let's show off invariants really quickly. So to kind of implement an invariant like the WETH balance, here I gave this example in the slides, but we might want to say a total supply invariant, which is like the WETH total supply is always equal to the balance of the WETH contract. Oh, maybe I'm a little zoomed out, by the way. Hope everyone could read that. So this invariant, now Dapptools should try to call our WETH function a bunch of times and see if it can break this invariant. Let's run this. So it's gonna first test our test deposit function, and that's gonna use our test invariant, and both passed. So what was that? 3 minutes. And we have a WETH contract that we just fuzz tested with invariants. Yeah, let's demo 1 or 2 more features. We might want to demo. I'm going to turn this back into a concrete test really quickly, just for simplicity. We can demo our dap test coverage view. So if we reset our terminal here and we write dap test coverage, you can see that our WETH.sol contract, we tested the deposit function, but we didn't test this withdraw function. So that's something we have to be aware of. We can try out the dap debugger really quickly just to show what that looks like. So we have this test deposit function, and we can kind of step through every part of it. So you can see this is the constructor being called. Let's just skip down the stack trace. Okay, now here's the juicy part. So we deposit, we call this mint function, we get the message sender, message.value. You can see the stack updating, you can see the opcodes going one by one. You can see it minting the token, and you can see the event showing up here on the right. So that's the debugger, that's invariant test, that's coverage, and this was all with straight out of the box Dapptools, no config required. So that is the end of my talk. I would go longer if I could, but yeah, I know that's we're already over.
Okay, thank you so much, Transmissions, for logging on and doing this really great workshop. Thank you for everyone who tuned in through Zoom, and thank you to the 20 or so other people who are watching from YouTube. I want to encourage everyone to, again, reach out to Transmissions, keep this conversation going, and yeah, have a really great day. Bye.
Thank you, everyone.